Alrighty, so in this video we're going to discuss radiation. What is radiation, how does it work, and what is it we need to understand to be able to discuss radioactive decay, nuclear decay, and things like this. So first of all, the main thing to understand is how atoms work. So an atom, of course, is a nucleus with little electrons orbiting around the nucleus. The nucleus is composed of protons and neutrons. And so, generally speaking, protons and neutrons are called nucleons. So when someone says there's a nucleon, what they mean is either a proton or a neutron. So the protons and neutrons, they're the nucleus, and in fact, the number of protons and neutrons describes the atom. And so, for instance, the atomic number is the number of protons. So, for instance, when we say hydrogen is the first element, or we say it's atomic number 1, that means it's got 1 proton. Helium, which is atomic number 2, the second element, it's got 2 protons, and so on. So the atomic number, sometimes it's called Z, defines the element you're talking about. So if we say element number 8, that means it is that element which has 8 protons. And all atoms that have 8 protons are all called that same name. So the number of protons, the atomic number, describes what the element is. There's also something called the atomic mass. And the atomic mass is the number of protons plus neutrons. So because electrons are so small, they have such a small mass compared to protons and neutrons, when we take the mass of an atom, we just ignore the electrons. They don't come into play. The main mass of an atom comes from its nucleus, and it's basically adding up the number of protons and neutrons gives you the atomic mass. Okay, so when we talk about hydrogen, the top number here is the number of protons, the bottom number here is the atomic mass. So this tells me it's got 1 proton plus neutron. And we already know from the atomic number that if hydrogen has 1 proton, that means it's got 0 neutrons. The normal standard hydrogen. Helium, we know it's got 4, let's say, protons plus neutrons. If 2 of them are protons, then you know it's also got 2 neutrons. Okay, that's atomic mass. So atomic number, the number of protons, atomic mass, the number of protons plus neutrons together. Now, one more thing, which is slightly weird. Obviously, we have number of protons is something, number of protons and neutrons is something. What about number of neutrons? What is that? That is called the isotope. It turns out that when you have an atom, when you have an element, We already know the number of protons describe what element it is. So let's say it's got 8 protons. Then it's atomic number 8, it's element number 8. But what about the number of neutrons? Well, it turns out it can have any number of neutrons. So for instance, let's take hydrogen as the easiest example. Hydrogen, 1, 1. That means 1 proton, 0 neutrons. Because its total mass is 1, and 1 proton I already know, so that means there must be 0 neutrons. What if we added a neutron? Now we would have something hydrogen 1 with a little 2 as its mass. Thus it has 1 proton because it's hydrogen. But now we know it also has 1 neutron. Well, is it still hydrogen? It is still hydrogen. The fact that it has 1 proton demands that it's hydrogen. However, this version of hydrogen and this version of hydrogen are isotopes because they have different numbers of neutrons in their nucleus. So the one on the right is heavier because it's got a neutron than the one on the left, which has no neutrons. But they're still the same element. And in fact, to differentiate it sometimes, and don't confuse this, sometimes we change the name if it's something that is important. So if it's useful in some way, we may name the isotope something different. And in fact, we do. Hydrogen 2 is sometimes called deuterium. Deuterium. It's still hydrogen, but just to denote it being the isotope with an extra neutron in it, we call it deuterium. And in fact, there's another one called hydrogen 3, which is 1 proton and 2 neutrons. Still hydrogen, but a really heavy version. This is called tritium. All 3 of these are hydrogen. They're isotopes of each other because they have different numbers of neutrons. Now, when you look at a periodic table, you'll usually see an average mass underneath. So you may see something like hydrogen 1, and then there's 1.00084 something underneath. And what this thing is saying is that if you take the percentage of hydrogen in the universe, that's hydrogen 1, plus the percentage of hydrogen that's hydrogen 2 or deuterium, plus hydrogen 3 or tritium, and you add all of them up and you average that total mass, this is the average you get. So obviously this is showing the vast majority of hydrogen in the universe is regular hydrogen. Because hydrogen 2, deuterium, would have an atomic mass of 2. And if there was a lot of that, then you'd expect the average mass to be closer to 2 than 1. And same goes for tritium. His mass is 3. So if there's a lot of tritium out here, you'd think the average mass of hydrogen in the universe would be close to 3. Here it's extremely close to 1. Now this number I've made up, but it's something close. And so what that means is most of the time you see hydrogen in the universe, it's hydrogen 1, regular hydrogen. But these other isotopes exist. And the same is true for every element. Every element out there has different isotopes. And in fact, as you get bigger and heavier elements, then you could get many, many, many isotopes of the same element. You know, when you start to get to things like element, let's say 38, I believe is strontium. Well, this could have anywhere between, 38 to, 90 neutrons. So you can have a huge amount of different isotopes for the same element. And so that's generally what you see. As you get bigger and bigger elements, you tend to get lots and lots of isotopes, different versions of neutrons. Now, the question is, why is this? What is the reason for these different isotopes? Why isn't it just like you would expect in an atom, when you have hydrogen, 1, that means you have a nucleus with 1 proton, and you have 1 electron going around. If you have helium, you have 2 protons, and let's say 2 neutrons, and you'd have 2 electrons going around. And lithium, you have 3 protons, 3 neutrons, and you have 3 electrons. So when you look at a normal atom, or normal element, the number of protons is the same as the number of electrons. They're electrically neutral. You have the same number of protons as electrons, unless you do something to change the number of electrons. It's just naturally, though, it's the same number. It's not true of the neutrons. The very first element, hydrogen, has no neutrons. You would think it'd have 1 proton, 1 neutron, 1 electron. That'd be normal. 1 of everything. And for helium, you'd have 2 of everything. And lithium, you'd have 3 of everything. But this doesn't work. It doesn't happen. The reason is because neutrons do something very specific, and it's important to see what these neutrons do. And it goes back to when we were discussing particle physics. I described, in talking about particle physics, something called the gluon, if you remember. The gluon was the particle version of the strong nuclear force. And I said what it does is it holds the nucleus together. Because check this out. If we think about helium, let's look at helium's nucleus. This will be helium. We have a proton, and a proton, a neutron, and a neutron, let's say. Nuclei are very, very small. They're much smaller than the size of an atom. The vast majority of an atom is empty space, so the nucleus itself is extremely small. What that means is you have 2 protons very close to each other. Now, we've all seen electricity and magnetism. We know that when you have a positive charge close to another positive charge, they repel each other. So how in the world can we have a nucleus with these positive charges? Remember, the neutrons are neutral. They don't give rise to charge. So what you have in this little bitty nucleus is a bunch of particles, all of which are positively charged or no charge whatsoever. So you would think this nucleus, there's no way it's going to stay together. They should all be repelling each other and blowing up. And that's what the strong nuclear force does for you. It overcomes the repulsion due to the electricity and magnetism, electromagnetic force. How does it do it? Turns out that if you take a positive charge and another positive charge, they're repelling, and you try to bring them close to each other. It's really, really hard to do, but it gets harder and harder the closer they are, because if you remember, the force, the Coulomb force, is K, Q1, Q2 over R squared. So the smaller this R, the closer they are, the bigger the force. So as I get closer and closer, it's harder and harder to do. However, there comes a point where if I get them close enough to just about touch, all of a sudden, this new force called the strong nuclear force takes over, and they hold on to each other, almost like they're glued together. So the strong nuclear force, what we learn from this is, number 1, it's very, very short-ranged. because you only feel it when these protons are close enough to touch. But number two, it's much stronger than the electromagnetic force, because that electromagnetic force is trying to split those protons away from each other, but the strong nuclear force holds it together anyway. That's why it's called the strong nuclear force. So, this is the strong nuclear force. It's exactly what it does. It allows charges, these or positive charges, or it also works for negative charges, let's say. It allows these particles, which should be repelling, to hold together if they're close enough. But what happens when we get a really, really, really big nucleus? Notice if we have a big element, maybe atomic number 50 or 60 or something. Well, now we have a nucleus with a bunch of protons all over the place. And let's say a bunch of neutrons too. Neutron, neutron, neutron. Well, first of all you have is a bunch of positive charges or neutral charges. So they should all repel each other. But I said, don't worry about it because the strong nuclear force holds them together if they're close enough. But notice, this proton, I'll do it in yellow, this proton here and this proton here are really far away from each other. They're not touching. They're not close enough to touch. So those two protons don't feel the strong nuclear force with each other. But they do, of course, still feel the electromagnetic force because that's infinite. You can feel that everywhere. So these two protons should be repelling the heck out of each other. And of course, this proton and this proton and this proton. They should all be repelling. Now, the ones that are really close to each other, this one with this one and with this one, they're close enough to hold together. But this red one and this one are not close together. So this is the secret to the isotopes. What happens is the neutrons also give rise to the strong force. So by placing a whole bunch of neutrons in there, you're putting more ability for the strong force to occur without increasing the positive charge. So you're basically putting in particles that give you more glue without trying to rip each other apart. If I try to put more protons in, yeah, I get more glue, but I also get more pulling apart action. And so it doesn't help anything, it makes it worse. But if I stick a whole bunch of neutrons in there, those neutrons allow the glue to stick together with everything without increasing the repulsion due to electromagnetic force. This is the reason for isotopes. The bigger atom you get, the bigger the nucleus, the more neutrons you have to feed in to stop that nucleus from decaying, from blowing up, and allows for more strong force to hold everything together. Okay? That's the reason for isotopes. And so, what winds up happening, let's say you have one of these big nuclei, and you have a whole bunch of neutrons in them, so it's stable, it likes to hold together, and then you take some of those neutrons away. Well, now, all of a sudden, you took some of the glue holding this thing together, it wants to decay, and it will decay, and that's what nuclear reactions are. At least one form of the nuclear reactions. So that's why you can get something like uranium, and you may have uranium 238 or 235. This one has more neutrons than this one. One of these is radioactive. It decays because of radiation, or decays by radioactivity. And the other one is stable, or at least more stable. It may not be perfectly stable, but one is highly, highly radioactive and the other isn't. And that's purely a product of the fact that one has more neutrons to hold everything together than the other does. So, I just want to make this video to explain a little bit about the strong nuclear force and how it relates to radioactivity, especially the whole isotope thing. What does isotope mean? What's the point of the neutrons? It doesn't have any charge associated with it. You can have something called oxygen, and it could have 8 neutrons, or it could have 3 neutrons. But it's still called oxygen. So, what is the importance of a neutron if it doesn't change the element? If I change the number of protons, I'm changing the element. Well, now we see the importance of the neutrons. They're there to give more ability for the strong nuclear force to hold this atom together, this nucleus together, and thus prevent radioactivity from occurring. If we get rid of some of these neutrons, then radioactivity is likely to occur. Now, next time, we're going to get into a little bit more specifics about radioactivity, what the particles are, what are the components of the radioactive decays, and see if there's different versions of radioactivity or if everything is the same type of radioactivity. So that you can look forward to next time, but until then, I'll see you next time.